try to be interesting. Dear Heavenly Father, we thank you for this day. We thank you for your students. Just pray that you'd help us to use this time wisely, Lord, just to glorify you, what we do. In your name I pray. Amen. So you guys had possibly a question about the upcoming and foreboding test, yes? Question number one, yes.
The first brand of question is vague-ish, but basically we were wondering, so for integral curves, you have to solve, or it amounts to solving like a system of differential equations.
Mm-hmm.
So as far as the test goes, we were wondering how much of differential equations should we brush up on? Like, are there some, I know some you just can't solve if it like works out that way, but is it mostly for like a lot of the curves we looked at? Like,
Well, I would hope you'd be able to solve ones like we did in class, mostly.
classic.
Yeah. I think the one that came up in the homework was unfortunate
Yeah.
because it actually required the full differential equations technique. I mean, the complex eigenvector plus or minus 2i, that was nasty. That was not my intention. And so, on the other hand, I would like you to be able to solve, for example, you know, or so I actually do, if you haven't had differential equations yet, I actually do want you to learn the constant and coefficient stuff for like quadratics, because that's what you need here. But again, that would, if you go back to the example we did in class, you'd be okay. I did say you can have a page of notes, right? Okay. So just to demystify this one, this is x equals to, c1 e to the 3t, y equals to c2 e to the minus 2t, right? So let's see here. In particular, if I had vector field x equal to 3x partial x minus 2y partial y, then the flow t x comma y would be what? I usually do I've been doing an extra step, like fitting this through x naught, y naught, x of times 0 equals to x naught. Well, that means that x naught is equal to c1, and y of times 0 equal to y naught. So that would be equal to c2 from these formulas. So if I'm looking at the flow time t through the point x naught, y naught, I get, x naught e to the 3t, y naught e to the minus 2t, like that, And then so I just swapped out my x naught, y naught for xy for the generic flow. Although, honestly, guys, this notation is not great. I mean, there should be like an upper sub x or something on here to indicate it's the flow of the vector field x. I'm sorry, it just bothered me. But we don't do that. I mean, you can do it if you want, but whatever. Now, this one over here, remember, the way we solve this is to go, okay, well, that means that dx dt equals to, that means ddt of minus dy dt is equal to y, right? Which tells me y prime prime plus y equals to 0. And so I hope you guys are math majors. You probably have noticed by now that the solution to this is c1 cosine t plus c2 sine t. And then, so if I want y of 0 would be c1, but I'm supposing that would be y naught, And what would x be? X is minus dy dt, which is what is it? Oh, yeah. So minus y naught sine t plus c2 cosine t, yeah? So x of 0 is equal to c2, which would be equal to x naught. And so you see that the flow, if we let y equal to y partial x minus x partial y, then the flow at time t through the point xy would just be what? Minus y sine t plus x cosine t, and then my y was y naught cosine t plus x naught sine t, I think. Did I get it backwards? Oh. Yeah.
Because you have x is minus with y, so it should be just positive with y naught sine t minus c2 cosine t. Because differentiate cosine to get minus and then minus of that is positive.
Oh. I see. It didn't hurt me in my calculation down there because we plugged it in 0, we got sine of 0, but it does hurt me when I go back to that. Yeah, thanks. That's supposed to be. No, we're good?
Should the other one be d minus?
Yeah, y sine t minus x cosine.
Oh, yeah, I'm sorry. Oh, did I failed to distribute this minus, haven't I? So that puts a minus here, and that puts a minus here. It's worse than what you guys are saying. So actually x naught was, C2 was minus x naught, which hurts me a little bit more than I thought at the start. C2 is minus, so I got a minus x cosine. Wait a minute. All right, scratch. Let's start over. Too many corrections. Let's try that again. Psi t of xy is what? So we could say x cosine t minus, yeah, plus y. So I've illustrated an important principle here is that hurrying wastes time. Let's see here. C2. Say minus x sine t. Okay. Oh.
You just plug in values for t to get different time flows.
Yeah.
Flow 1 and 2.
So that's a circle.
So that's when we're saying that x and y are equal to x naught and y naught.
Yeah. I don't want to do that before because I'm using x as like the formula for the parameterization of the integral curve. But then here I'm using xy as a fixed point that we're flowing along the vector field, you know. So anyway, getting back to your question is no, differential equation is not a prerequisite for this course. So as much as I would love to just write down anything I want and then just let you guys go nuts on it, that would be foolish on my part. Now, on the other hand, I could ask a careless question where I say, set up the differential equations whose solutions are integral curves. That is reasonable for everybody, no matter what I do. So what do you think, guys? Would these flows commute? Yeah, what would be the, so if I ask you, if I was to ask you, you know, is it going to be the case that psi sub t composed with phi sub t is equal to phi sub t composed with psi sub t? there are two ways you can go there, right? The one way you could do is just calculate both flows, right? Like, imagine yourself in a world where we actually hadn't calculated the flows yet, right? Put yourself in the place where all you were given is the vector fields x and y, and you're asked, do the flows commute? You know? Then it would be very foolish to calculate the flows and then check it directly, right? The way faster way to do it would be to check by the theorem and see if it's the case that the Lie bracket, the commutator bracket, is that 0, right? I don't think these are 0, no, but I haven't checked. I'm just not sure right offhand. So.
And that's only the case for the Lie derivative of a vector field in the direction of a vector field. That's the only case for its Lie bracket. If you take Lie up like a form, you have to use Cartan's formula.
Right, yeah, Lie derivative of a form, we got to use Cartan's formula, and it's lots of different flavor choices there. Lie derivative is a very general concept that looks quite different on different objects, yeah. That is true. All right, one down. It's very satisfying. Next question. This is so weird. Students have actually brought questions to the review date. Like, this is unprecedented. It warms my heart. This is reason enough for a pizza party, I think. Yes.
On Monday, is it?
Instead of the test or during the test.
The person who eats the most slices gets an A on the test. I don't know. It's like books can be deceiving.
Doesn't eat anything in a weekend. What are you doing?
You know, it's true. It is absolutely true. The guy that was smallest in my Bible study in college, he's the one that could, like, put away the most at CC's. It was ridiculous.
My book was 5'4", and she beats me in eating.
Well, you've seen those hot dog contests. You see who wins it, right?
I think it's the same guy for the last 15 years.
See, to me, that's more respectable than, like, I don't know, LeBron James. Or whatever. You pick your favorite sports, or Dale Earnhardt. I'm sorry, rest in peace. Dale Earnhardt Jr. or Jeff Gordon, or any. You pick your favorite sports. Like, to me, the guy who can eat the hot dogs the fastest. I mean, that's something we all do, right? You know.
That's true. There's a bigger pool of people who eat hot dogs
Yeah.
So it's more
than other
impressive.
sports.
Really impressive.
Right. Hot dog eating, it's the people's sport.
It's out of all the people who participated in eating hot
It's a very fast.
Yes.
Yeah, if you win at NASCAR, it's like being the first finisher in a one-person race.
Yes. See, I know there are other questions on that page, right?
Oh yeah, there's many.
Okay, go ahead.
Okay, the next one was, so pullbacks.
Yes.
We know, and push forwards, they're grouped together. So the calculation is, we don't have to do those in here. Some of the questions are pretty straightforward, but we were wondering, like, what in the theory should we be studying? Because the calculations are one thing, but then understanding, like, how they, the things they work with.
Let's see here. So, like, what are the? It's a good question. I guess the question is kind of like, what are properties of the
Or, like,
push forward?
theorems that we would need to prove regarding them.
Oh,
Proof or no, I guess.
Yeah.
I mean, certainly, I can think more of pullback. For some reason, push forwards. There's got to be something to say about push forwards. I mean,
You can write pullbacks in terms of push forwards.
I guess just the definition of push forward would be good, right? If I have f going from m to n, right, and I talk about the push forward of v, right? So here, v, I can do v sub p if you like. V sub p an element of the tangent space P of M, right? Then what would this would be an element of what? This would be an element of the tangent space at F of P of N, right? How do we define that? Like, we let that, we think this is derivations, right? Derivations on C infinity F of P, right? It's derivations of the smooth functions defined near F of P on the manifold N. And so in order to make sense of this, we should say how it differentiates such a function. Let's call it G, right? And so what is it? Yeah, VP of G composed with F, I think is correct, yeah. So G composed with F is what? This is a mapping from M to N to the reals, right? So that makes sense. That's great. That's the definition. How do you actually calculate it? In coordinates, what does that look like, right? I'd like to say, suppose we have M with coordinates x1 through xn, right? And we're going to N with coordinates y1 through ym. Again, my function f. Excuse me. Then, if we calculate the push forward of, let's say, x, I guess capital. Let me use capital V for a change, right? So what that means, how you actually calculate it is, well, first of all, I kind of have to give you some fine print here. V is itself the sum I equals 1 to n of the, let's say, upper I partial xi, right? I'm suppressing the point dependence here, right? I mean, there probably should be of p. I mean, x, partial xi p there. You'll forgive me if I omit that here. Now, so it works out to the sum j equals, well, I equals 1 to n, sum j equals 1 to m, and then what you have to do is the partial derivative of the ith, rather the jth coordinate of f with respect to xi. That gets, and I forgot to put my kind of important vi here. Oops. So sorry. I think I did that wrong. No, yeah, I'm sorry. I just a second. Wrong. So what are you telling me, King? I think it actually is VI here, right? And partial, I believe it's partial of, I think I was right actually, yj composed with f. My index is up all of a sudden, what do you know? X, oh, look, my index just went up on the x too. Isn't that interesting? Sorry, I have failed to commit to an up-down index notation in here this semester. My apologies, but I'm not holding you to it either, so there you go. Except where I actually use it in a specific and technical and actually meaningful way, where we're talking about the sharp and flat maps, and that was something we covered and worked with, so sorry about that. Rest assured, where I'm being careless about the index up and down is a place where we're not thinking about the sharp and flat map. This is not good. I must remedy this in future offerings of this course. I'm sorry. Hopefully it won't end up confusing you anywhere. I don't think it will, but yeah, there actually is that's actually the formula for calculating it in terms of coordinates. So
y upper j composed of f might be written as f upper j.
right, that is the jth component of f, right? But I think I've given you guys a bunch of. I won't give you another example. I don't think I need to go over an example here. We've had a lot of examples of this, but.
Don't smooth functions pull out a bit too?
Right, that's the thing is if we you can see that here too, right? If I take this g and I multiply it by a smooth v and I multiply it by a smooth function g, well, that just puts a g here, right? And so yeah, you can pull that out, right? And you can see that this would be equal to g times the push forward of v.
So really, you're just pushing the basis.
Yeah, it's not really differentiating the vector that it's pushing. In some sense, it's differentiating the function, right? I mean, that's right.
That's something I was wondering when I ended up getting stuck and stopping on problem 70 is the push forward different from the tangent map, or are they in the end the same? Because they're both written very similarly and they seem to have very similar definitions.
I think the push forward and the tangent map are the same thing up to an identification. So tangent map, what do you mean by that?
Like if you have, like you said, f from n to n, and you
Yeah.
just write f lower star.
I mean, I had what I was agreeing to was earlier in the course I talked about, we had f as like a mapping of normed linear spaces, say from V to W, and I talked about DPF
Right, and that's
as
you write
mapping.
that as f lower star in the book, right?
Right, and so I would say that DPF is really the same as F star at P in a sense.
Okay.
And but some people would disagree with me. I mean, the numbers kind of, well, okay, so there's an abuse in some sense, well, because the differential, I mean, if it's the F star is a mapping on tangent spaces, right? The reason that these could be compared for normed linear spaces is we identify a normed linear space with its tangent space.
Right, and the book does that in 4.13 and 5.34.
You can actually find other advanced calculus books where even for normed linear spaces, they say that the differential acts on the tangent space. So there's not a universal agreement about how exactly, where the line in the sand should be drawn and the abstraction should begin and the numerical convenience should end. I mean, that's a numerical convenience to identify V with its tangent space. But this is really more intended for explicit approximation of functions from one vector space to another, whereas this is something that's more used in terms of like abstract differential geometric reasoning. But they're not unrelated. I mean, this is still the best linear approximation to F in the abstract sense. I mean, it is that.
So you break them down and they're combined.
Yeah.
Whatever representation like you do there, they're the same.
Yeah. I mean, tangent space is a linear approximation to the manifold. I mean, that's not incorrect. Just I don't usually think of it in terms of approximation. I don't know. But that's still there to use. Maybe I should think about that more. But you can ask other questions like, what's the best second linear approximation? What's the best quadratic approximation to a manifold? Could you deal with, what would that mean something? Okay, well, I didn't answer the question. That's the push forward. So basically for push forward, I don't know, I mean, there are some basic properties like, you can pull functions out. It's linear, right? The push forward, like if I had f plus g star, it would be f star plus g star. There's some nice things like that you can see relatively. The pullback, of course, has much, much more to play with, you know. So pullback, on the other hand, so here we're talking f, say going from m to n again. So f pullback, oh, wait a minute. Yeah, f pullback of omega is an element of lambda k m when omega is an element of lambda k n, right? Now, I mean, some people have this idea, and I think, for example, John Lee, who wrote Smooth Manifolds, I think he'll say, he thinks of F star for pushing forward vector fields, whereas the differentials at a point, he likes to think of F star as something that we use to push vector fields from one manifold to another. And that's okay in as much as, at least it's locally okay. I mean, if F doubles up on itself somewhere, then you could have the push forward of a vector field not be a vector field, right? I mean, I think that there's an issue.
Isn't that like one of the conditions on that? Or is
Yeah. Oh, I don't think there's any, I mean, I think we just need F. I think we define push forward as long as F is differentiable. I don't think I insisted F be injective. So F not being injective, it can hit the same point 2 times for 2 different values and approach it in a different way from those different values and consequently produce different tangents at that single point. Yeah. I mean, we could take a simple example. Suppose that F is just a path, you know. You could have the image of the F look like this, right? And so it could be that the push forward of one vector looks like that, but the other one looks like that, you know? If I had F going from, say, R to R2 with a point of self-intersection, then if this might be F push forward of, you know, partial t at time 1, this would be F push forward partial t at time 2.
Yeah, that's really weird.
But that single point in the codomain, I've attached 2 vectors, so it's not going to be a vector field in R2 that I'm pushing forward. It's
Yeah, because in the definition it seems like you're right, but then once we express in terms of those coordinate functions, like that seems like it gets rid of any sort of ambiguity because it's explicit.
Well, it's just the issue is that the issue is buried. The issue is not apparent in my formula here, Sam, because I failed to write the thing that matters, which is f of p. The issue is that this f of p can be the same even though p is different. That's just a function theoretic thing. That's not a... Yeah. Pullback, on the other hand, well, we're okay. Pullback of a form is a form. It could be 0, right? But it's a form. And so what were the most important properties of pullback? Well, there are many. The pullback of the differential of alpha is differential of the pullback of alpha. Woohoo! That one's kind of nice. I use that to calculate a lot. Pullback plays nice with the wedge. if I have alpha wedge beta, it's the pullback of alpha, wedge the pullback of beta, right? If you have the pullback of a function times a form, that's also, f pullback g times f pullback alpha. So here, I point that out that I've tried to put forward the viewpoint that this is really just a special case, special case of the above, all right? But just to be clear, just to make sure we're all on the same page, a function scalar multiplied by a form is a wedge product in a kind of stupid, trivial sense. So it's still, you still have this. But what is that actually? What's the pullback of a function? It's just composition, right? Did I go right the way? Or is it f composed of g? I can't remember. Okay. At least you guys got it together. Very good. All right. Well, I'm not taking the test. You guys take the test. So that's good. Anything else? I don't know. There are others. It's got nice distributive properties. The interior product, it plays nice with that too, and it's in a natural way. And then we had the more specialized discussion. If we have a diffeomorphism, we can pull back mixed tensors by a combination of push forward and pull back at the same time, right? So if we have a mixed tensor, not a form or a vector, but possibly both, or I guess you could just have a vector and pull back a vector. You can do it by basically pushing the vector back with the inverse. So we can use an amalgam of push forward and pull back if we have a diffeomorphism to take vector fields or tensors of mixed type and move them one side or the other. The larger point is if you have a diffeomorphism, you have the same differential structure on both sides, and you can use the diffeomorphism to transport it in kind of ways that you would be natural. Sorry. Yeah, another question. I'm blathering on about this one too long.
So for the generalized Stokes theorem, because we don't know boundaries too well, is that something we won't be calculating with?
Well, but I think you can still do the generalized Stokes theorem, you say you don't know boundaries, but I think they're just kind of natural. Admittedly, I'm a little bit leery of them since we haven't delved too far into the details there. But if I gave you, let's just try to think of let's think about a volume in R4. Something like so inside R4, we could look at the volume formed by taking the unit square at the point 0, 0. And we could take that and we could take the Cartesian product of that and I don't know, how about the S1 well, I meant is you guys, this is not a good thing. Let me make up an example on the fly here. 0, S1, 0 maybe. I'm trying to think about this. Not sure I like that. think I've gotten something clear yet. Oh, forget this. This is not the way to talk about it for you guys. How about a volume? T, X, Y, Z, right? Such that 0 less than or equal to T less than or equal to 1, and X squared plus Y squared plus Z squared less than or equal to 7. Sure, why not? I believe this is a volume. Yeah. This is a three-dimensional manifold in R4. And I could ask you, what's its boundary? I mean, it's not a manifold in the open sense of manifold. This is a closed manifold.
So the boundary would be t is 0 or t is 1 or x squared plus y squared plus z squared equals 7.
Or x squared plus y squared plus z squared equals to 7. Yeah.
Anything that's in V satisfies bounds.
Right. Am I sure that's a 3 manifold?
I can take in the same one as in three-dimensional, and this is
Isn't this a 4?
I think it's a 4 manifold. I think you're right, yeah. I should have put equal to 7, yeah. There we go. Now it's actually a 3 manifold. It's a sphere of radius root 7 attached to T, right? What's that? Yeah, maybe to understand this better, it's helpful to think about like a W, which would be something like TXY, such that 0 less than or equal to T less than or equal to 1, x squared plus y squared equals to 7. Now we can visualize it, right? So if this is T and this is y and this is x, so what is x squared plus y squared equals to 7? It's a circle, right? And what we're doing is we're attaching a circle at each point. Well, it's really, I can't,
So you made
it's a pillbox, yeah.
The boundary of that would be the or
Yeah, so the boundary of that is definitely the caps on the side, right? I mean, there's actually 3 pieces. There's the back, there's the front, and then there's that piece. I mean,
now does that one, because you were describing a two-dimensional surface, right? So the boundary of it would be
oh, I'm sorry. You're right. You're right. I didn't say x squared plus y squared less than or equal to 7. You're right. You're right. It's not a. I said cylinder, but I should say what? It's not a cylinder. It's a. Well, we call that a cylinder. It's an open cylinder. It's a cylindrical shell, if you like, but shell of. You're right. You're right. So Sam, I think you're correct. The boundary on that one is just this and that, right? And so the V is harder to picture, but the boundary is actually, even if you can't picture it, you can kind of see what the boundary would be. What would the boundary of V be? Yeah. Basically, it's 0. If you allow me that notation, I mean, I'm saying the sphere in x, y, z coordinates. Is that? Yeah, so I'm sorry, V is 4-dimensional, right?
Not this one.
This V is this V is 4-dimensional.
That is three-dimensional because the spheres are two-dimensional. They're not balls.
Oh, stink. So that's 3-dimensional. The boundary is 2-dimensional. Whatever I do, if we get a boundary which is not lower dimensional, we're in trouble, is my point. Fine, Cooper, you've made your point. I should probably not ask about a calculational. We probably have not done enough of these to make it a reasonable test question, but now you give me a challenge. How do I write a reasonable test question on the generalized Stokes theorem? I think the answer is I'd be sufficiently vague that I ask about properties, right? Like, while it's difficult to ask about a specific example, if I say, I don't know, prove the analog of integration by parts for generalized Stokes theorem, that problem you could do.
You could workshop it for the next 2 years.
Workshop it. You know what I'm saying? Like, suppose you wanted to integrate alpha wedge d beta, and over I don't know, over m. How would that be related to the integral of beta wedge d alpha over m? How are those related? Generalized Stokes theorem allows you to relate them. Ordinary integration by parts, you've got integral of u dv equals to uv minus integral of v du. This is from a to b, this is from a to b. What's this? In the middle, we have evaluation from a to b, right? But this is actually the integration of uv on the boundary of a to b. And this is actually the integral over the line segment a to b of u dv in differential form notation. Anyway, you could derive what I haven't written by simply looking at the product rule, the Leibniz rule for wedge product, right? So if I was to ask a question about generalized Stokes, I would like you to know generalized Stokes theorem, know what it says, and be able to use it symbolically, or if I do enough hand-holding with a specific example, but, you know.
You said that minus would mean the one with minus one. I mean, the d alpha wedge beta.
D alpha wedge beta, what was it? D alpha wedge beta plus minus 1 to the what? P of alpha wedge d beta, right? Where P is what? For alpha a, what would you say, Travis? Number of, it's the degree of alpha as a form. So alpha is a P form. So if alpha is a 1 form, get a minus there. If alpha is a 2 form, we get a plus, so forth. All right, what's your other? Is that? Yes, there's more. Okay.
The co-derivative was
Ah.
from mission 6.
Yes, the co-derivative is interesting. I do not remember its formula right offhand, but you can tell it to me. Delta of alpha is equal to? Some stuff. All right. Minus 1 to the what?
I don't know the n, but I know n
Okay, so for our R3, let's say, for R3, it's, star d star alpha. I've written those as stars as to not confuse them with the push forward or the pull back. And also, this is a metrical thing. I mean, this assumes a choice of metric. In particular, I'm assuming the Euclidean metric on R3 when I write that. The Hodge dual is a metric-dependent thing. So what's your question about it?
Just so we have a formula, so its interplay with like work forms and flow forms and stuff, is that something we should know? Because like, was it the co-derivative?
I think it's something I might ask you questions about. I don't know if you should know it ahead of time or not. I mean, if you know, like, what are the basic things about work forms and flux forms? I mean, I think the basic thing was that the work form of ABC, right, is ADX plus BDY plus CDZ, right? And the flux form of the vector field ABC was A dy wedge dz plus B dy wedge dz. What? dz wedge dx plus C dx wedge dy. So the work form, the flux form.
Oh, right. Yeah, it was the co-derivative of the...
Who did we just, who was missing?
I was missing.
You were missing. Okay. I was like,
And to where the
oh, okay. I remember she. Well, she warned me ahead of time, but I was like, I was wondering. Every once in a while, the janitor gets antsy and he just really wants to get in here and clean, and like they'll just keep popping their head in the door, you know. One semester, I met with a student every Monday and Wednesday and Friday from like 4 till 5:30. It was this class actually. Before 4:50 happened, and it was just him and me. But every single day at like 4:50, the janitor would like open the door and then like ask a question about if we're going to be in here a while, and like, yeah, and like he would do it every single class. I got so annoyed. I don't have that problem anymore. They're much better behaved, but yeah. Where was I? So this is the work form, that's the flux form, and you know, the simple way to remember what Hodge duality says, it says that the Hodge dual of the work form of a vector field is the flux form of the vector field. The Hodge dual of the flux form of a vector field is the work form of that same vector field. I mean, that's Hodge duality in a nutshell. That's the interesting part of it. Of course, there's also that the Hodge dual of a function is the function times dx wedge dy wedge dz, and then the Hodge dual of another function times dx wedge dy wedge dz is just the function. I mean, that's Hodge duality in 3 dimensions over the Euclidean metric in a nutshell. That's it. So if you really understand those and you can work with those, you know, calculating what does the coderivative of something look like, it's not too big a deal. Like, what's the coderivative of a function?
well, the Hodge dual function is the free form, so you differentiate it, you get 0, right?
Very good. Yep.
And the Hodge dual of the free form is the co-derivative of the free form is the gradient.
Yep. So, yeah, it's not especially exciting because the coderivative takes your form degree and lowers it by 1. So if you start out with 0 form, you got nowhere to go but 0. There are no -1 forms in R3, right? On the other hand, if we were to calculate the coderivative of, say, omega, of a vector field, well, that's interesting, right? Then that would be Hodge dual of the differential of the flux form of f, right? And it seems likely at this point in the test, I've already asked you to prove that the differential of the flux form is what? Yes, the divergence of f times the volume form, yes. Yeah. So this is just the divergence of the vector field time, well, it's just that. So this is a 1 form, that's a 0 form, right? So the coderivative of work form is actually the divergence of the vector field that that corresponds, yeah. Yeah, there's about a half dozen interesting questions to ask about coderivative. That would be good test questions, yeah. I wouldn't try to figure them out before I asked them. I would just like face it on the test and enjoy it if I were you. I mean, if you want to try to play the game of figuring out what I'm going to do, you can do that if you want, but that's not really what I'm after in here. Yeah.
He literally hand listed every single theorem from his notes.
I did do that. That's true. Yeah, differential equations is it's a little different ball game in there, but yeah. Yeah, I think to not think about that in differential equations would be folly, because differential equations got time pressure and yeah. But you also have a formula sheet in there, at least for one of the tests, so.
No, we bullied you into having one for all of them.
Oh, you did?
Yeah,
Oh, man.
you forgot to take it off the syllabus.
Dang it.
So we called you out on it.
Oh, man. Someone read my syllabus. Why? That's what
It was
surprising. Danica was in there. Oh, my goodness. The legendary Danica. Let's see here.
I was reading your syllabus just the other day, and it said at the bottom, I reserve the right to change the syllabus at any time.
That is true. That is in all of my syllabuses. So I'm guessing you have another question? 3 more. All right. I better bide my time. All right. Go for it.
The curvature question is just, so using that K formula from the really long one.
Okay. The K formula based on E, F, G, and company, yes?
Yeah. So the question on that was, is it true that we can write every metric? Because I know you can work it out in the problem at least, where the matrix of the metric is just E, F, F, G. And so if basically you could give a metric, I could write that and then calculate the curvature.
The matrix of the metric is what?
E, F, F, G.
E, F,
It worked out,
FG,
I tried
yeah.
out 3 metrics and it was the case for all 3.
Yes, that is, yeah.
And so then the curvature, the Gaussian curvature is simply just that formula. That's it.
That's right. Yeah.
For everything.
Mm-hmm. Yeah, that's the point. Is before we had all this intrinsic, beautiful mathematics, we had formulas, and so that formula is the curvature. Yeah.
It's funny that he works out homework instead of in the actual chapter. He just puts it at the end.
Right. Well, that's the change in viewpoint. So if you look at older books, you'll find that what's in the chapter is not present at all And it's just about that formula and explaining why that formula has properties that it does and so forth. Yeah. Okay, next question.
All right, you can instead pick your fourth again. So the one question is on exactness and closed forms.
No, you can ask both the questions. I wasn't saying you have to.
No, just whichever order.
Oh, okay.
And the next one's on parallel transport.
Oh,
Whichever one you want first.
parallel transport. So what's your question about parallel transport?
Basically, if me and Jonathan were studying it, and could you just do like a short example on one, or you don't? I know there's formulas he has for like, for specific cases. There's like it comes down to solving the differential equations.
Right.
Set of them.
Yeah.
Computationally, but
There's one in addition.
yeah.
Was that one of the specific cases?
Which mission was that in?
Yeah, 7. Or was it 7?
Yeah.
7, yeah.
Ah, curses, I don't have that worked out yet.
Yeah, I guess it was still over. Could you just explain the basics again? I'm just like kind of cloudy on parallel transport in general. Like, I know there's a lot of theory in it.
Yeah. Give me a second here.
Because I understand the geodesics thing, but parallel transport is kind of sketchy.
I should say one of the things I like that you guys haven't asked me about was this finding the gradient. You know, that gradient, find the gradient. That's a really neat application of everything we've done. Where's that? I think it's Theorem 5.46, really. Tells us what's what, right? It says UG, a Riemannian space with corresponding Riemannian connection nabla. Then if we have C, it's from 0, 1 to U, smooth, curve, what? C of 0 is P, with C of 0 equal to P. And if we have V naught, an element of the tangent space at P to U, then there exists a unique parallel vector field V, right? Such that V of 0 is equal to V naught. And the vector field V, this is called the parallel transport of V naught along C, right? Let's see here. I'm trying to remember. Was equation 5.8, those are the ones we need to solve?
Yeah.
So basically, to actually find that parallel transport, we have to solve this system of differential equations. So, yeah, it's kind of tough.